Okay, this example is taken from a book in volume 1, problem 126. The claim here is the Serie, that is 1 over 1 times 2 plus 1 over 2 times 3 plus dot plus 1 over n times n plus 1 is equal with n times n plus 1. So in other words, this we can take the last term here and we can write as a sum. K is equal 1 to n, 1 over k times k plus 1, which we can write the same terms in the same form. N is equal to then divided by n plus 1. So this series just I'm rewriting in a different form. And we want to prove does this series hold? Is this true or false? So let's go to the next slide. Proof. Let's prove by the induction. So first of all, we have the series, what we already got from the question. And first of all, let k is equal with 1 and let n is equal with 1. In this way, we are taking just the first term. That's what we have here, 1 over 1 times 2. And we are taking the right side here, and we plug in n is equal with 1. Here is 1. 1 plus 1 is 2. So that's what we have. 1 over 1 times 2 is equal with 1 over 1 plus 1, which implies 1 over 2 is equal with 1 over 2. So when k is equal with 1 and n is equal with 1, it holds. So now let's go back and let's check when k is equal k plus 1 and n is equal n plus 1. So with the first method here, if we are plugging in when n is equal with n plus 1, so let's go to the original. Here instead of the n, we are plugging n plus 1, which is going to be like we have here, n plus 1. And down here we have n plus 1. If we are plugging here n plus 1 is going to be n plus 2, what we have here. But we want to prove, does this hold? When k is equal with k plus 1 and n is equal with n plus 1. And when we prove this, we write this series in this form from k equal with 1 to n plus 1. So, and we are exchanging here. What we are going to get, we are adding one more term. And here is a k plus 1 times a k plus 2, what we have here, this. And this implies is equal with n over n plus 1, because on the left side, we are adding this term here. You see this term here. This is an extra term, what we are adding on the left side. The same thing we are adding on the right side of the same term. So that's what we are doing here. And now what we have to do for equating k is equal with n. Let's take a k is equal with n. And here what we have, n over n plus 1 is equal plus, instead of the k, I'm plugging here 1 here. And what we get, n plus 1 times n plus 2. And in this fraction, the LCD is n plus 1 times n plus 2. So to make the same here, I add here n plus 2 and here n plus 2, which we already, when we clean up a little bit with the algebraic work, we get n times n plus 2 plus 1 divided by n plus 1 times n plus 2. So now what we're going to do, we already have to distribute here. N times n is n squared, and n times 2 is 2n. So this is going to be n squared plus 2n plus 1, what we have in the next slide here. N squared plus 2n plus 1 divided by n plus 1, n plus 2. But this one here, when we factorize, is going to be n plus 1 times n plus 1, which is n plus 1 squared. And now this square here, we are simplifying with n plus 1. And what we get here, n plus 1 time over n plus 2. So it holds because of the side here. When we looked here, for example, when we plugged was 1 plus 1 n over n plus 2. And here we are proving when we are applying n plus 1, n is equal to n plus 1 and k is k plus 1 by induction. We already get this side. That's why we are saying here when we plug n plus 1 in this case here, in this case we got this formula was n plus 1 over n plus 2, and when we apply the by induction it holds when n is equal with 1 and k is equal with 1, and when k is a k plus 1 and n is equal with n plus 1, it holds. Therefore this series here, this series, the sum of this series is equal with n divided by n plus 1, so it holds.